Welcome to the World of Groupcraft 5 conference. And this is the third session of this conference. The first speaker of this session will be Dr. Swarup Bhowmik. He is a postdoctoral fellow at the IISER Bhopal institution in India. And he will be speaking about quasi-isometric groups of Euclidean spaces. Over to you, Swarup. You may begin.
Thank you, Samoda. Okay, so good afternoon, everyone, and thank you, Somoda, and the other organizing committee for inviting me for this type of international conference, World of Groupcraft 5. Okay, so I'm Swarup Bhowmik. I'm from IISER Bhopal, and okay, let us start the talk. So this is the title of my talk, that quasi-isometric groups of Euclidean spaces. So, and these are the quick outlines of my talk. That first we go to, as usually, introduction, and since the keyword of my title is that quasi-isometry, so first we go to the definition of quasi-isometry. I hope you all know, but actually quasi-isometry means, roughly speaking, you can say that is a map which basically preserve the shape of a space at large scale. It actually doesn't care about the small details. It only cares large scale. So now we go to the formal definition of quasi-isometry. So basically, it's a map from a metric space X to X prime, said to be, suppose, first quasi-isometric embedding. If this relation, this inequality holds for all x1, x2 belongs to X, basically this is a distort. The distance actually doesn't distort too much. This inequality says, and also if this map is code surjective, that means for any element in a codomain set or X prime, you can say that if we get another element X belongs to the domain set such that the distance is in between fx and y should less than a constant, then we can say that this f is a quasi-isometry. So if f is satisfies these two inequalities, then you can say that f is quasi-isometry. So when basically two quasi-isometric are equivalent, here two quasi-isometry, suppose same from same space to same space, that x to x, f and g are said to be quasi-isometrically equivalent if if distance of fx of gx less than a constant which is greater than 0. So if this condition holds, then we can say that f and g are equivalent. So it can be checked easily that this relation is an equivalence relation. And suppose now we forming the quasi-isometric group. So since this is an equivalence relation, so let class F denote the equivalence class of F of the quasi-isometry F from X to X, and we denote the basically set of all classes by classes of quasi-isometry basically of X by QIX. So QIX is the equivalence classes, and this set usually forms a group with respect to our usual mapping composition. So this is a group QIX. So if we take X equal to real line, then it will be QIR. And if it is Rn, then it is QIRn. So this is a formation of group. And instead, there are the two facts that if there is a suppose quasi-isometry H from X to X prime, then the quasi-isometric group QIX, because for a metric space X, we can form QIX, for another metric space X prime, we can form QIX prime. So if there's a quasi-isometry from X to X prime, then the two different groups QIX and QIX prime, they are actually isomorphic. This is a result. And therefore, if we can get easily that T goes to box T is a quasi-isometry from the real line to the integers, so we can say the quasi-isometric group of the real line and quasi-isometric group of the integers, they are isomorphic. So these are the quick things. Now we go to basically some known results of QIR. That means why basically QIR is so important, or why we can study about that group QIR. So the basically the first information, one of the first information, not the first, first interesting information is proved by Sankaran, that there is a natural homomorphism phi from PL delta to QIR, which is surjective. So here basically PL delta means the set of all piecewise linear homeomorphisms from the real line to real line, such that the slopes are bounded of that functions. So this map is surjective. That means you can think about QIR as a PL delta R. So this is the first information. And also he proved that several remarkable groups like diffeomorphism of S1, the lifting of that group, or PLS1 of the lifting, and Thompson group, and even a free group of rank C. These type of groups are embedded in the group QIR. That means this group is very much rich, and also we can study about the group. And in this talk, actually, we want to characterize the group element of that group QIR and some properties of that group. So these are some well-known results. Also, in 2016, Chakraborty proved that interesting fact: the center of the group QI is trivial. So this is also an interesting fact. And next, in recently, they proved that the orientation preserving quasi-isometry group that is left orderable but not simple. It's a useful fact of that group QIR. And also, they proved that this group, orientation preserving quasi-isometric group, cannot act effectively on the real line R. So these are some well-known results about the group QIR. So in this talk, we want to mainly structure. Go to structure of that group QIR. I mean, what are the actual elements in terms of slopes we can see actually of that elements of the group QIR. So first, one thing is noted that they Ian Zhao in 2023 they proved that the group QIR is isomorphic to QIR plus. R plus means basically the quasi-isometric group from the positive real line to positive real line, and direct product QIR minus semi-direct product the reflection. So this QIR group is isomorphic to this. So if we see this isomorphism, so if we only characterize the group on the positive real line, the QIR plus, that is enough to study the whole group QIR, because QIR plus and QIR minus is isomorphic and so on. So basically my main aim from now that we want to characterize the group QIR plus, and that is the quasi-isometric group of the positive real line. So next, they give an interesting thing that this group QIR plus is not simple by providing this type of normal subgroup that H equal to all those quasi-isometry such that limit is 1, limit fx by x is 1. So this is the result. And similarly, we can show that the group QIR minus is also not simple by using a similar type of normal subgroup that H prime looks like this. And also it can be checked that the direct product of H and H prime also a normal subgroup from of the group QI plus R by taking that H bar equal to all those quasi-isometries as the limit is mod x tends to infinity if x by x is 1. So these are the some quick results from the observation. So now basically we want to characterize this group by using an invariant. We introduce first an invariant, and then we break the group QIR plus into smaller units and then characterize that units. So what is the invariant? We first introduce this invariant that Sg equal to limit n tends to infinity gxn by xn such that this sequence is convergent and xn tends to infinity for any class G belongs to QIR plus. And it is well defined, that means if class F and class G are same, that means AF and G are in the same equivalence class, then the limit set of SF and SG, they are also same. It can be checked. So this is the invariant, and we see that this set SG is a compact and connected subset of the positive real line. So this is a good observation that since it's a compact and connected subset of the positive real line, we can say that this set is either a singleton set or maybe or a interval. So for the singleton set, we just define all those quasi-isometry such that the limit is the C only point. So HC is equal to all those quasi-isometry such that SGC. And also HI means all those quasi-isometries has the limit set of that quasi-isometry is the interval I. And it is clear that HC bar is equal to union of that HC, C belongs to R, and it is clear HC subset of HI and QR plus equal to union of I subset of 0 infinity HI. So these are the some observation. And now we go to some the technical part that suppose for a quasi-isometry G, SG is AB in the interval A comma B. Then always we can get an element, this type of FA inverse belongs to the HC type of set, HA inverse, such that the limit set of FA inverse compose G that is equal to 1 comma A inverse. That means if you take any element in the quasi-isometric group, always we can construct and this type of element Fa inverse compose G, this type of elements whose limit set is 1 comma something. So again, since HC bar is a subgroup of QR plus, we can basically construct QIR plus quotient HC bar that is equal to disjoint union of H1 comma something quotient H. So basically we break that group QR plus into QR plus quotient HC bar, then from to H1 comma M quotient H. So now we want to characterize in the group in the set H1 comma M by H. So for that, suppose two elements F and G are in the set H1 comma M quotient H, and if they are in the same class, same H class, basically H equivalence class, then you can write class F is class of H compose G. And moreover, if a sequence goes to infinity, then limit n tends to infinity Jn by n equal to 1 implies if n by 1 equal to 1. So if no sequence this type of an is exists such that this limit is 1, then they are in different class. So on the other hand, if we take a sequence such that this Fan by n and Gn by n is 1, we are taking this. Okay, so Fan by n and Gn by n is 1 for this type of sequence, then we can say something about their slopes F and G, and they are in same class or not actually. If they are in F and G are in same H class, then what is the actual criteria on the slope of that F and G? That is my main aim. That what is the slope condition may differ of F and G for being that F and G are in the same class, same equivalence class of H. Okay, so that's now we go to the main result of this section, that structure theorem. So first we go to an equivalent criteria that suppose HF and HG belongs to, or F and G belongs to belongs to that H1 comma M quotient H. Then F and G belong to the same equivalence class if this relation holds. That is fx by x minus gx by x less than epsilon for all x greater than m. If this is hold, then we can say that F and G are in the same H class. So by using this lemma, we basically construct this theorem that if two elements HF and HG belongs to that H1 comma M quotient H, and if this is my condition, I impose this condition that there exists a sequence n for which Fn by n and Gn by n goes to 1, then if norm of an minus bn tends to 0, what is n minus an and bn? N basically the sequence of slopes of f in the interval n comma an plus 1, and for bn it is g. That means bn with the sequence of slopes in the interval n comma n plus 1. That means in the interval n comma n plus 1, we basically partition on the interval some finite partition xn, x1, x2, x3, and in that partition basically this is the slopes an for f, bn for g. So if the difference of their slopes and the supremum of that slopes, basically this norm tends to 0, if this happens, then we can say that f and g are in the same equivalence class of H. But the converse is not true. That means if f and g are same equivalence class, then it may not be tends to 0 with an extra condition, that the condition is that there exists a constant k1 for which the next partition element, and xni should be greater than k1 xni minus 1. This xni xni minus 1 basically the partition in the interval an comma an plus 1. So if this relation holds and f and g are in the same equivalence class of H, then we can say that the difference of their slopes f and g in that interval n comma n plus 1 goes to 0. So these are the structure. Why it is needed? Because Bhowmik proved that there is a surjection or surjective homomorphism from the group PL delta to QIR. But it is not proved that when two representations are in the same class. So here we can check partially that if this relation holds, then we can say that they are in the same class. So this is the need for our case. Now we go to quickly our some dynamical properties of that group, quasi-isometric group QIR or QIR plus. So left tolerability and local indicibility of the group QIR. So what is left tolerable group? You know that a group which left tolerable means it admits a total order and it is left invariant. So this is the definition, usual definition. So what are the quick examples? That all torsion-free abelian groups, free groups, braid groups, these are the examples. All the homeoplast, real line. These groups are the example of a left orbital group. And what is the non-example? Any finite group, finite index subgroup SLNZ, these are the left orbital, non-left orbital group. So now we go to the definition of locally indicible group. So a group is said to be locally indicible if basically each of its finitely generated subgroup, from that subgroup to Z, there is a homomorphism. Not only homomorphism, non-trivial homomorphism to Z. So then we can say that this group is locally indicible. And then go to the quick examples, that torsion-free one-letter groups, the braid groups B3, B4 only, that they are locally indicible. And non-examples are the braid group Bn or in regular 5, and all non-left order groups, they are not locally indicable. So now we go to a criterion for checking left orderability, because to check a group is left orderable or not by using this definition is quite hard. So that's why we go to a criterion that is by Navas, that a group is left orderable if and only if for every non-trivial elements there exist choices between 1 and -1 such that the identity element is not the semi-group generated by that gi to the power epsilon, g1 to gk are the non-trivial elements. So if this identity is not an element of this semi-group, then we can say that the group is left orderable for any collection on trivial elements. So by using this criteria, it can be checked a group is left orderable or not. This is quite feasible. Okay, next we go to some facts that every locally indicible group is left orderable, but the converse is not. So we basically here provide some counter example in the form of QAR plus percentage. Okay, so for the first we proved that the quasi-isometric group QIR plus percentage, that is left orderable, and we proved this result by using that Navas criterion. That we take some non-trivial elements from that group, and then by using induction and some taking a word of that elements, and we prove this left orderable. This is not easy to prove that, but it is quite large. By using that Navas criterion, we proved it, not by the definition. And we know that any left orderable group is torsion free. So we can say that the corollary is the quotient group is torsion free. And then we go to quickly to some remarks that the QI plus R quotient H bar. H bar means that the previous H bar, that QI plus R quotient H direct toward QI R minus quotient H prime. So we know that QI R plus quotient H is left orderable, and they are basically isomorphic. We can check. So QI R minus quotient H bar is also left orderable, and any direct product of left orderable groups are left orderable. So we can say QI plus R, then we are preserving from the real line quotient H bar, that is also left orderable. And next we see that an element f x equal to minus x. So the order of that element is 2. So this is also in QI R quotient H bar, because this is a reflection element. So when it is a reversing element, so QI R quotient H bar in that set, in that group, the element has finite order. So it is not left orderable, because if it is left orderable, then it is torsion free, but this element has a torsion, so it is not left orderable. And also it is not locally indicible, because if it is locally indicible, then it is left orderable, but it is not left orderable. That's why it is not locally indicible. And also we prove that the quasi-isometric group QIR plus quotient H is not locally indicible. So these are the some results of this section. First, we prove the structure, partially, not fully, but structure of the group QIR plus, or you can say QIR plus quotient H or HC bar. And then we then we prove some results about the group QIR plus quotient H. So left orderable, torsion free, or local indicible. These are the results from this section. Now we go to the higher order. That means the group QIRN. So in this section, basically we first introduce a notion of piecewise linear homeomorphism of the real line, or or PL delta Rn in the form, because in the real line we see that PL delta R means the set of all piecewise linear homeomorphisms of the real line with bounded slopes. But what is the intuition of PL delta Rn? So this may be quite extension of that PL delta R. And then by using that, we provide a criteria, combinatorial criteria on the vertices and edges of the simple cell structures to provide whether basically a piecewise linear homeomorphisms to be a quasi-isometry of Rn. And that means which elements are in the set QiRn or group QiRn, and also find the center of the group QiRn. So what is PL homeomorphism of X? First, we fixed locally LFSC space, that means locally finite simple cell complex K naught of X, and the homomorphism G is said to be piecewise linear with respect to that K naught. If we get a two locally finite simple cell complex K1 and K2, which are equivalent to K0, and there is a simple cell isomorphism from xk1 to xk2 such that G realized by F. So this set of piecewise linear homomorphisms with respect to K0 is noted by PLX, K0, and there is a homomorphism from the free product of this PLX, K to homox. So the image of that homomorphism is the PLX. And similarly, we can define PL delta X. So what are the extra condition? The extra condition is all those elements in PLX, K naught are in PL delta X, K naught. If the first two conditions are satisfied, the second one is that for each simplex delta belongs to K1, and for all xy belongs to delta, we can find that 1 by m less equal to distance of gxy by distance of xy less equal to m. Almost the real line version, that in real line PL delta R means piecewise linear homeomorphism, the bounded slopes. So here basically we extend that idea that distance of gxy by distance of dx is bounded, and here all the elements xy are the elements of the simplex. Okay, so and similarly there is a homomorphism from the pre-product to homox, and the image of that this homomorphism is PL delta X in the homox. So now we prove this lemma. The lemma says that if X is a path connected LFSC space with the piecewise metric dp equivalent to the Euclidean metric d, then the set PL delta X is a subgroup of bilipsages. We prove this, and since we know that any element in bilipsage X, basically that is a quasi-isometry. So if this is a corollary, that if X is a path connected space with the piecewise metric dp equivalent to the Euclidean metric d, and if an element G belong to PL delta X, then that element is a quasi-isometry of X. The corollary. So now we basically define two sets A and B. A actually defined by the angles, not only angle, cosine of the angles between the adjacent edges of the simplex. So that is for K1 it is A, and for K2 it will be B. So define in that way. And next we so the commutational criterion. What is the criterion? That here if X is a LFSC space and if G be a piecewise linear homeomorphism with respect to K naught only. If this happens, then again if the relation says that distance of GPI GVJ by distance of VIVJ. That means only if we know the information about the vertices of that simplex that is bounded, and if the two sets defined A and B, these are closed subsets, then we can say G belongs to PL delta X. PL delta X means basically that this first inequality satisfies for all the elements in the simplex. But if we know the information about only the vertices, then it is enough to say that G belongs to PL delta X. So these are the result. Next, we similarly so that if X is a path connected space, in previously proved that X is a path connected space, LFSC space, with the length metric dp is equivalent to the metric Euclidean metric d, and if G belongs to PLX, K naught, we prove that G if this relation holds, that means the vertices and edges are bounded by 1 by mu and mu, then G belongs to PL delta X. We proved previously, but also we proved that if X is path connected in LFSC space, then PL delta X is a quasi-isometry. So G belongs to PL delta X, that means G is a quasi-isometry of X. So now if we just modify X by Rn, so if G belongs to PL Rn, then this relation again holds A and B, then we can say clearly that G is a quasi-isometry. That means this what are the quasi-isometry group, what are the elements in the quasi-isometry group of Rn? That are the elements. If G belongs to piecewise linear homeomorphism of Rn and satisfy these relations, then G is a quasi-isometry of Rn. and G is quasi-isometrically equivalent to the entity map if and only distance of FVI and VI is less than constant. So this is the main result of this section. Also, by using this result, we prove the center of the group QIRN is also trivial. So it is also interesting because in the one-dimensional case, that means that for QIR, Chakraborty proved that only the center of the group QIR is trivial. But here, using this criteria, we prove that the center of the space in general, actually QIRN, that is also trivial. So these are the main information about the group QIR and QIRN we just studied. And this is the last section. And now this section, first two sections basically published on geometry dedicated, and the second one is published in topology applications. And these are the quick references which basically we used for our paper. This is references 1, and this is from references 2 we used for this talk also, and this is the references tree. And this, thank you.
Thanks, Swarup. Any questions? I have a question. So,
Yes,
do we know about the center of, say, QI of S1, the circle?
I don't know. We can check it. We can just study it QI S1 because for RA it is trivial, but for in general space we don't know. We have to check it. Okay, that QI S1, the quasi-isometric group of the S1, center of
Correct.
that group actually what should be. Okay, we can. I don't know actually what is the exact center of that group. I only studied about the real line and Euclidean space, but we can check it for so it's a good thing,
So,
I think.
so
Yes.
QI of S1 and QI of R, you said QI of S1 is embedded in QI of R, is it? Or in one of the
QI,
slides you
no, that is actually PLS1, piecewise linear
PL,
of
acha,
S1.
PL. I see.
PLS1 and the lifting maybe lifting PL the lifting of that group embedded in the group QIR actually. They
Okay.
someone proved this result.
So between QI S1 and QI R, do we have interesting maps?
It may be, but I don't know actually. Uh, okay.
Okay.
I don't know about the relation between the group QI S1 and the group QIR, but
Okay. No problem. So
we should think
Yanis is
about.
saying that he wants
Yes,
to
yes,
see
yes.
the slide of references.
References. Yes, yes. Just
Can you go back to the slide on references?
is it now visible?
Yeah. So
These
this
are
is
references which I used for my paper mainly. And also we are working on the group QIRN explicitly. That means we want to find the normal subgroup of that group QIRN because it is known that H is a normal subgroup of QIR plus. So basically we want to characterize the group QIRN now. Now I am just working on the group QIRN only. That what may be the normal subgroups, if there is a normal subgroup, what are the normal subgroups actually, what are the collection of normal subgroups, and what are the property of the normal subgroup. That means is it left tolerable, is it locally indivisible or not. We are just now working on that group QIRN, but QIS1 we can also think about that group also. This may be an interesting fact. But for real line and RN, it is quite difficult to study explicitly. So
uh-huh.
first we just uh, discuss about only the real line and Euclidean spaces. Then we can think about that group QIS1 for your question, Shomula.
Right. Right. Any other
And
questions? Quick questions.
Hello, am I audible?
Hi, yeah, Pavitra.
Yeah, nice talk, Swarup. I have a very basic question. In the definition of a quasi-isometry, so the
Hmm.
constants are generally different, right? I mean, you have taken both to be m.
Yes. You can think actually it is quite loose. I can take that constant also. I know that it is MC quasi-isometry. You are saying AC quasi-isometry or something, etc. We can relaxing that constant. We can take that. I'm taking in that way actually.
Okay.
It can be done.
Okay. Thank you.
Right. Also.
All right. Thanks a lot, Swarup, for the very wonderful talk.
Thank you, Somoda.
You can unshare. Yeah, please stop sharing.
Yes. Now is it okay?